Welcome back to the Deep Dive. Today, we are jumping into something you probably touch dozens of times a day but never really think about. The hidden rules of plastics engineering.
That's right. Specifically, injection molding.
Exactly. When you pick up, say, your laptop, or even just a bottle cap, you're holding a piece of design that follows a completely different rule book from metal or wood.
It's a whole different world. Our mission today is to, well, cut through all the dense design guides and give you the core insights, the things you absolutely have to know to design a plastic part that actually works.
One that won't fail or warp or, cost a fortune to make.
That's the crux of it. See, unlike metals, they're complex, they creep over time, they shrink like crazy as they cool, they react really strongly to temperature.
So if you just design it like a metal block, you're doomed.
You guarantee failure. So we're going to unpack the absolute must-know principles, starting right at the foundation. Walls and corners.
Okay, let's start there with maybe the biggest rule that just throws traditional engineers for a loop.
Mm-hmm.
If I want a strong piece of metal, I just make it thicker. A solid block.
Right.
But if I try that with plastic, if I try to mold a thick, solid piece, I'm already in trouble. Why is mass basically a four-letter word here?
It all comes down to heat. Plastics are, well, they're terrible conductors of heat, just awful.
So they hold on to it.
For a very, very long time. And a thick section takes forever to cool down. That kills your production time, drives up costs. But the real problem is structural.
Okay.
As that big mass of plastic cools, the outside skin hardens first, right?
Yeah.
But the inside is still molten and it's shrinking. It pulls the hardened surface inward, and that's how you get those ugly sink marks. Or even worse, you get voids, empty pockets inside the part.
Which you can't even see until the part just snaps in your hand.
Exactly. So the whole mindset has to change. You have to avoid solid chunks. Every single part, no matter how tough it looks, should be designed as a thin shell. Cored out, hollowed.
Exoskeleton.
A perfect analogy. And with that shell, rule number 1 is non-negotiable. Keep your wall thickness as uniform as you possibly can.
Because if one part is thicker than another.
They cool at different rates. And that means they shrink at different rates. That creates internal stress, and the part just twists and warps itself into something useless.
So what are we talking about thickness-wise? What's the target?
It's a pretty tight window. For, say, a glass-filled, high-strength material. You're aiming for somewhere between 0.75 millimeters and maybe 3 millimeters.
That's thin.
It is. For unreinforced stuff like polypropylene, you can go a bit thicker, maybe up to 5 millimeters. Right. But if you absolutely have to change thickness, it cannot be a sharp step. It has to be a gradual ramp or a gentle curve.
You have to ease the material into it.
You have to give the cooling rate a chance to transition smoothly.
Okay, so that handles the flat surfaces, but then you have to make a 3D object, which means corners, and a sharp corner, which might look really clean and crisp in a CAD model.
Is a mechanical failure just waiting to happen?
Why is that?
Because plastics are what we call notch sensitive. A sharp internal corner is a perfect stress concentrator. Any load you put on that part gets focused right into that tiny point.
And it cracks.
Immediately. But it's also a manufacturing problem. Think about it. A sharp corner, that's material overlapping. The thickness right in that corner can be almost 1.5 times your nominal wall thickness.
We're right back to the sink mark problem.
Back to sink marks, long cooling times, all of it. The solution is mandatory. You have to radius the internal corner.
So, round it off.
Round it off. The rule of thumb is the internal radius should be at least half the wall thickness. But ideally, you want it to be more like 60 to 75% of the wall thickness. That's the sweet spot for flow and for stress.
But if I round the inside, what about the outside corner? Doesn't that just make the wall thicker as it goes around the bend?
That is a fantastic question. And it's a subtle but absolutely critical rule. To keep the wall perfectly uniform, the external radius has to be equal to the internal radius plus the wall thickness.
So you're adjusting both to maintain that perfect uniform shell.
Precisely. You eliminate the stress point without accidentally creating a new thick spot.
Okay, so now we have our optimized thin shell, but it still needs to be strong. Since we can't just make it thicker, we have to add internal supports. We have to add ribs.
Yes, the I-beam principle for plastics.
Exactly.
And ribs are just incredibly efficient. The stiffness you get from a rib is proportional to the cube of its depth.
The cube, wow.
The cube. So if you double a rib's depth, you make it 8 times stiffer. It's a massive multiplier, which means deep, thin ribs are always better than short, thick ones.
Go deep, not fat. I like that. But then you have to worry about where the rib meets the wall, right?
Right.
That connection point can't be too thick.
Or you'll see it on the other side, a sink mark right on your pretty cosmetic surface.
What's the ratio there?
The rib itself should only be about 50 to 75% as thick as the main wall. And then you add a small fillet radius at the base. If you stick to those rules, the root thickness stays under control and your surface stays clean. And don't forget, you need to add a draft angle.
So it can actually come out of the mold.
About 1 degree per side is perfect. Otherwise, it's stuck in there for good.
Let's move to bosses.
Okay.
These are the cylindrical towers for screws and fasteners. They seem unavoidable, but they're also a big, thick chunk of plastic by definition.
They are a necessary compromise, but we manage it. You never leave a boss standing alone. You support it with buttress ribs, maybe 3 or 4 radiating outwards.
And if it's near a wall,
You tie it to the wall with a flat rib. You're trying to spread that mass out to anchor it and manage the stress.
and the type of screw you use matters immensely depending on the plastic.
Absolutely. It comes down to the material's flexural modulus. How much does it bend? For softer, more flexible plastics, you want thread-forming screws. The plastic actually flows around the screw, forming threads without cutting away material. No little bits of plastic swarf.
And for hard, brittle stuff.
It's like a glass-filled nylon. It won't flow, it'll just crack. So for those, you need a thread-cutting screw that carves its own way in.
You also can't just drill a standard-sized hole. The material itself tells you what the hole size should be.
Right, using something called a hole factor. The design guides will tell you, for example, that ABS has a factor of 0.80, but polycarbonate is 0.85.
Meaning the polycarbonate needs a slightly bigger hole for the same screw.
Because it's harder and less forgiving. It's all about fine-tuning that engagement.
But the real killer, the thing that causes failures years down the line, is creep.
Yes, the silent killer of plastic assemblies.
If a screw is holding, say, a dashboard in place for 5 years in a hot car, I can't just use the material's day one strength to calculate how well it holds.
You absolutely cannot. If you do that, the boss will fail. The material slowly deforms under that constant load. That's creep. It relaxes its grip.
So you have to look up long-term data.
You have to use the 5-year or even 10-year stress value from the material data sheet. A plastic's immediate tensile strength might be 35 megapascals, but its 5-year value could be as low as 15.
If you ignore that, the part starts rattling itself apart a few years later.
That's where all those mysterious squeaks and rattles in old products come from. It's creep.
Okay, let's switch gears to features that actually move. The living hinge is probably the most famous one, that thin little web on a Tic-Tac box lid.
A beautiful piece of engineering. And its secret is all about material choice and processing. The material is almost always polypropylene. It's just a champion at resisting flexural fatigue.
And the hinge itself is incredibly thin.
We're talking 1/4 of a millimeter, maybe 1/2 a millimeter thick. But the processing is where the real magic is.
You have to make the molten plastic flow across the hinge, not along it.
That is the single most important rule. You want to align the long-chain polymer molecules in the direction of flow. So when they're aligned across the hinge, they act like tiny fibers, giving it incredible tear strength when you bend it.
If you get the flow direction wrong,
It'll snap on the first or second bend, so your gate location is everything. You can't have weld lines or any kind of flow hesitation right on that hinge.
is there a post-molding trick for them?
There is. If you manually flex the hinge a few times right after it comes out of the mold while it's still warm, it sort of cold draws the plastic, aligning the molecules even more and making it stronger.
That's fascinating. What about things that are in constant rotation, like plastic gears and bearings?
That's a whole world of heat and friction management. For bearings, it's all about the PD limit.
Pressure times velocity.
Right. You multiply the pressure from the load by the rotational velocity. If you go over the materials limit, it generates heat faster than it can get rid of it.
Right.
Then it softens, wears out, and fails.
And the shaft material matters too.
A hard steel shaft is usually best, but some of the lowest wear combinations are actually plastic on plastic. An acetyl bearing on a nylon shaft can be incredibly durable.
And then for gears, they have to be perfectly symmetrical, I imagine.
Or they'll wobble and destroy themselves. Asymmetrical cooling leads to a warped gear, so you need symmetrical flow in the mold. The best way is a single gate right in the center.
And if you can't do that,
Then you need multiple gates, perfectly spaced, and never ever just 2. You need at least 3 to balance the flow pressures. Then, of course, you have to de-await the theoretical tooth strength for things like fatigue, temperature, and shock loads.
Right, so once we designed all these amazing parts, we often have to join them together, and there's so many ways to do it.
A huge variety. We can start with welding. Ultrasonic welding is very common.
High-frequency vibrations.
Exactly. It creates friction and heat right at the joint. It works best on rigid, amorphous plastics like ABS or polycarbonate because they transmit the vibrations really well.
And you often need to design in little features to help it along.
You do. They're called energy directors. Tiny little V-shaped ridges that focus all that vibrational energy into one spot for a fast, clean melt.
What about something more exotic, like induction welding?
That's a really interesting one. You actually place a special material, a ferromagnetic bonding agent, inside the joint.
So it has iron particles in it.
Yes, then you hit it with an alternating magnetic field. Only the agent heats up, melting the plastic around it. The best part is you can take it apart later by just applying the field again. It's great for repairs.
Yeah. Let's talk about the dark side. Chemical joining, adhesives, and solvents. This brings up the biggest boogeyman in plastics failure.
Environmental stress cracking, or ESC.
It's the #1 cause of failure, isn't it?
By a huge margin. It happens when you have a plastic part that's under stress, and that can just be the residual stress left over from molding, and it comes into contact with some kind of fluid.
Not necessarily something that would dissolve it.
No, it's not a chemical attack. The fluid just gets into microscopic surface cracks and accelerates their growth catastrophically. Common cleaners, paints, even some adhesives can trigger it.
So you have to know what your part will be exposed to over its entire life.
You have to. Amorphous plastics like polycarbonate are notoriously susceptible. We saw massive failures in the early days, safety glasses cracking just from being near paint fumes.
Any materials that are safe.
Polypropylene is the superstar. It's virtually immune to ESC. But for other materials, when you design an adhesive joint, you have to think about the forces. They're great in shear, terrible in peel, so you need a lap joint, not a simple butt joint.
Okay, one more quick one in this area. Powder injection molding, PINEM. This isn't for typical plastics, right?
No, this is for making really complex parts out of metal or ceramic powder. You mix that powder with a polymer binder to create a feedstock that you can injection mold.
What's the hardest part of that process?
Getting the mix right, a perfectly homogeneous blend. If the powder and binder separate at all, the final sintered part is garbage.
So how do you solve that?
Often with something called split feeding in a special extruder. You feed the waxy lubricant part in first, let it coat the machine screws, and then you add the heavy ceramic or metal powder. It reduces wear and gives you a much better mix.
We're really seeing how design stretches from the macro all the way down to the molecular. Which brings us to the end of life. Design for environment.
A modern imperative. You have to think about recycling from day one.
Rule #1 must be labeling.
It is. You have to mark every part with the resin identification code, the little number in the triangle so sorting machines know what it is. And rule #2 is you have to eliminate or at least minimize all the non-plastic bits.
Screws, clips, paint.
All of it. Anything that has to be manually removed is a contaminant and a cost.
So how do our assembly methods stack up for recycling?
Well, snap fits and press fits are the gold standard. They're easy to take apart. Welded joints are harder to separate. But if the plastics are compatible, they're okay because there's no foreign material.
That's a good point. Now, for our final topic, let's look at the ultimate in parts integration, outsert molding.
This is where you take a rigid metal base plate and you mold all the complex plastic features, bearings, gears, springs directly onto it.
You get a super rigid multifunctional component. But there's a fundamental conflict at its heart.
A huge one. The plastic shrinks as it cools. The metal does not.
So the plastic is trying to pull away from the metal it's anchored to.
And that stress will either warp the metal plate or just shear the plastic anchors right off.
How on earth do you manage that?
It takes some clever tricks. For bosses, you need to anchor them through holes in the plate and use those buttress ribs to stop them from twisting as they shrink.
Okay.
And if you have a long wall feature, you can't mold it as one continuous piece. The cumulative shrinkage would be too much. You have to break it up into short, separate sections.
So each little section manages its own shrinkage without affecting the others.
Exactly. And maybe the most overlooked part is the runner system that feeds the plastic.
How does that play a role?
If you use a standard straight runner, it shrinks too. And it pulls on the part you just molded, creating stress. So for outsert molding, you have to design flexible runners, S-shaped or diagonal.
So the runner itself can bend and deform as it shrinks. absorbing the stress instead of passing it to the part.
That's the idea. It decouples the shrinkage of the feed system from the shrinkage of the final part.
That is just an incredible level of detail. I mean, we've gone from the radius of a corner to the danger of cleaning solvents, all the way to the shape of the channel that molten plastic flows through.
It shows you can't treat these as simple materials. They're dynamic. The real art of plastics design is that you're constantly balancing these opposing needs. The need for strength today versus the long-term reality of creep. The cost of a fast cycle time versus the risk of molded-in stress.
And the best designers are thinking years, even decades ahead.
They have to be. They're not just thinking, does this work now? They're thinking, how will this perform after 5 hot summers in a car? And how can someone easily take this apart and recycle it in 10 years? That's the real deep dive.
I think next time you pick up any product around you, you're going to look at that rounded corner or that little plastic nub in a completely new light. Thanks for taking this deep dive with us.